Hi all. We discussed theoretical concepts related to heap in the previous videos, right? Now let's solve few problems related to the heap so that we'll get better understanding. So for that we'll solve a problem, kth largest element in an array. This is on lead code. So if you read the problem statement, you are given an integer array names and an integer k, and you have to find the kth largest element in the array. So there is an array which is not sorted, and you have to find the kth largest element. So suppose we'll start working on this array. This is my array and I have to find the third largest element. So by looking at the array, third largest element is 10 because 20 is the first largest element, 15 is the second largest element, and 10 is the third largest element. So my answer on this array is 10. So there are different approaches to solve this problem. So I have listed out here three approaches, and there is one more approach called quick select. Since we have not spoken about quick select, I did not mention that approach here. When we talk about quick select, we can solve this problem using that approach as well. For now, we'll concentrate only on these three methods. One is using sorting, and the second one is using maximum heap, and the third one is using minimum heap. So first we'll talk about sorting approach. Sorting approach is nothing but you take an array, you sort it. Now my array here is 7, 10, 4, 3, 20, 15. 3, 20, 15. Now I'll sort this array in an descending order, sorry, 20, 15, 10, 7, 4, 3. So after sorting, my array looks like this because I sorted my array in a descending order. And when to find the kth largest element, what you have to do, the kth largest element is this one. Third largest element is 10. So since array index starts from 0, 0, 1, 2. So my kth largest element lies at second index, which means so after sorting the array, you have to fetch the k minus 1th index element in an array. So we have done two things here. One is you sorted the array, and then you fetch the k minus 1th index element value from the array. So for sorting, whatever the algorithm we use using the bubble sort, selection sort, or the heap or merge sort, the time complexity of sorting an array is order of n log n, right? So the time complexity to sort this array is n log n, and time complexity to fetch k minus 1th index is order of 1, because since array is a contiguous location, it won't take you much time. You can fetch the k minus 1th index using a constant time. So my time complexity here is order of n log n, and the space complexity for sorting is order of 1. We are not using any extra space here. Whatever space that takes for sorting, we have to consider that. So that is order of 1. So when we see the time complexity, can we even reduce that? There is one more approach where we can use heap, via which we can reduce the time complexity better. So okay, we'll use maximum heap first. So as soon as you look at the problem, the first intuition that comes to a person when we think about heap is kth largest element, right? So what we can do is we can create a maximum heap. So what I can, using an array, I create a maximum heap, and then since I need a kth largest element, I pop out elements. So my intuition here is, now I created an array. I created a heap using that. When created a maximum heap, I'll have the largest element, first largest element at my root element, and then I'll have the remaining values here. Now I'll have 10 here, and 7 you'll have here, and 4 you'll have the downwards, right? So when I created a heap, might be I'll have 7 here, and then I'll have 4, I'll have 3 here. This is my maximum heap. So when I create a maximum heap, since you don't need the first largest element, you need the k largest element. So I have to pop out. So since I need the third largest element, I have to pop out 2 times, k minus 1 times, because first I'll pop out. When I pop for 20, second largest element comes here, 15 comes here. Now I pop out 15. When I pop out 15, third largest element comes here, 10. So since you need the third largest element, after popping k minus 1 times, kth largest element lies at the root of a maximum heap, and directly you get the top element of the maximum heap, and that would be your answer. So this is one simple approach using the heap. Let's see the time complexity and the space complexity of this approach. If you see the space complexity, you are creating a heap of n elements. So my space complexity would be order of n. Okay, here I have written space complexity is order of n. And if you talk about time complexity, you have done two steps here. One, you have created a maximum heap, and then you have deleted k minus 1 times from the heap, right? So creating a heap, as we discussed in previous videos, using heapify method takes order of n, because n is the number of elements. If you create a heap with k elements, this would be order of k. So here we have created heap using complete array. This is order of n. This is for creating heap. And you have deleted heap. Deletion operation in a heap takes order of log n time, right? We discussed this already. So deletion takes order of log n. Now how many times you have deleted? You have deleted k minus 1 element. So my time complexity here would be k minus 1. So if you see the combine both time complexities, order of n plus k minus 1, order of k minus 1 log n. So here k minus 1 order of k minus 1 log n. So this is reduced a little bit, because let's say my k value is less. K value, if you say the k, even if you see here, this is n log n, which is very higher. For let's consider n is 10. So my value would be 10 log n. Let's consider here my k is 2. Okay, then here what would be my answer? K is 2. 2 minus 1, 1, right? So order of log n. Here the k minus 1 value comes out to be 1, and order of log n, log 10. So for n value 10, this would be 10 log 10, and here for this would be order of log 10. Log 10 is here, log 10 is just time complexity here, and here this is 10 log 10, which is higher compared to this approach. So it depends on k value. If the k value is larger, let's say my k value is 9, then it will become 8 log 10. So if for small, like it, but in any case, if the k value is very small, this would be even lesser compared to sorting approach. If k value is higher, then this time complexity increases, but it is lesser than this. So in any case, the time complexity is lesser compared to the sorting approach here, right? But if you see the space complexity of this approach is order of n. So but in the sorting approach, this is a order of 1, right? Can we reduce this space complexity? Yeah, we can do that. We can do that using a minimum heap. So what is the intuition of using minimum heap? First, let's see how to use a minimum heap, and then we come to the time and space complexities here. Okay, now one thing, when we see this array, we have created a heap of n elements. Now we just need the kth largest element. When we see the problem statement, we just need the kth largest element. You don't need all elements in a sorted order. You don't need an array in sorted position. You just need a kth largest element. So do we really need to create a heap of n elements? Because my space complexity would be order of n in that case. Do we really need a heap of n elements? We can reduce that. So what I'll do here using minimum heap is, my intuition of using minimum heap is, you need kth largest element, right? So what I'll do is, let's say my array contains 1 to 10 elements, integers 1 to 10. So since I need third largest element, what I'll do is, I'll store three larger elements in my heap. So 1 to 10, 8, 9, 10 are the three largest elements, right? So what I'll do is, instead of storing 1 to 10 and then fetching the kth largest element, what I want to do is, I'll just store only 3 elements. Since k is 3 here, I'll just store only k larger elements in my heap, and then I'll fetch the minimum element of this. So I repeat, since I need only the third largest element, what I am doing is, I'm storing only k larger elements in my heap. So out of 1 to 10, I have 10 integers here. I need not store 10 here. I'll just store 3 larger elements, which are 8, 9, 10. Now I need a third largest element. So I don't need the first largest element, second largest element. I need the third largest element. So third largest element is the minimum value in this heap. So two things. First, fetch k larger elements, add k larger elements to this heap, and even in this heap the my value would be the minimum value. This is my intuition of using minimum heap. So to solve this, what I'll do here is, first I'll create a heap of k. I am not creating heap of n elements, I'm just creating the heap of k. I'll add first 3 elements or first k elements to my heap. So what I'll do here is, so I'm traversing this array 7, 10, 4. First I'll add 7 to my heap, and then I'll add 10 to my heap. Now when I added 4 to the heap, this doesn't hold the minimum heap property. For minimum heap, the root value would be the minimum of all its children, right? So I swap these two, 7 and 4. So my 4 will go here and 7 will come here. So this is my minimum heap. So till now 7, 10, 4, I have the 3 larger elements in my heap, and the minimum element would be the kth largest element, right? So the kth largest element is 4. Now I'll add one more element, 3. So while adding, if you remember, I need k larger elements. This heap should contain k larger elements. So if the value I'm going to, if the value I'm traversing is larger than the root value, then only I should add to this heap. Otherwise, why I need not add it, because now my value is 3. So obviously 3 is not my larger element because I have k larger elements here. If I'm adding one more element, this should be larger than these elements. This should be larger than this k4. See, if it is lesser than this, I need not add it to my heap. So when I traverse 3, this is lesser than my root element. So I will not add it. Now the next element is 20. 20 is greater than 4. So 20 is greater than 4. So till this is my array till now, right? 7, 10, 4, 3, 20. My 3 larger values would be 27 and 10. So 4 doesn't hold true now. So what I'll do is I'll remove this 4 and then I'll add here 20. Now my root element would be 20. Okay, but this is not my minimum heap, because in the minimum heap this should be the minimum value. So what I'll do is I'll do the adjustments here. 7 will come here, 7 will come here, and then 20 will go here, 20 will go here. So my minimum heap would be 7, 10, 20, because till now my 3 larger elements are 7, 10, 20, and this is a minimum heap. 7 should be at the root position. Okay, done. Now the next element is 15. So I'll compare 15 with 7. So when I compare 15 with 7, 15 is larger than 7, right? So this is not the third largest element anymore. So that's why what you'll do is you will swap it. So I'll swap this. 15 will be at my root. But when you add 15, is this a minimum heap? No, 15, 10, 20. 15 is larger than 10. So what you should do is you should swap 15 and 10. So my minimum heap now would be 10, 15 and then 20. So this is my minimum heap, and I have done traversing the array, and the root element after solving this for all elements would be my solution. So third largest element here is 10. So this is using the heap. So if you see here, we have reduced the space complexity. You have not created a heap of n elements. You just created a heap of k elements. So space complexity for a minimum heap is just order of k. And if you talk about the time complexity, initially we have created a heap of k, and heap creation time complexity is order of k, and then you have swapped elements. So when we my total array value would be n, right? So already you have created heap of k and the remaining elements would be n minus k. So n minus k into like let's suppose these n minus k values are greater than the root every time, and then you keep doing this pushing operation, then my time complexity would be n minus k log k. Okay, so you understood it, right? Because you have created a heap of k and the remaining elements are n minus k. Now all these n minus k elements are larger than the root value. So what you have to do every time, you have to swap the, you have to remove the root element and replace it with the new element, right? When you do that, this doesn't hold minimum heap property anymore, and you have to push your larger elements to the downwards. So that operation, like deletion operation in a heap, takes log k time because my heap size is k. That's why each deletion operation takes log k time, and we are doing it for n minus k elements. So my time complexity would be n minus k log k. If you see here, we have improved space complexity from the previous approach, and even the time complexity wise, when we compare, the k value is always lesser than n value, right? So here you have log n, here you have log k. Either it would be lesser than or equal to n. So my time complexity is also improved here. We have moved from log n to log k, right? So these are the three approaches of solving this problem. Now let's solve this using Java. So I'm not solving this using the sorting technique, because anyway we can use the util provided by Java arrays.sort of. I'm not talking about that implementation. I'll solve this problem using maximum and minimum heaps. So as discussed in the previous video, we spoke that priority queues can be implemented using heaps, right? So here for using a heap, we use the priority queues. So first we are solving using the priority queue. By default, priority queues follows the minimum heap property. Now since I need the maximum heap, I have to specify it here. Let's do that. So this is my priority queue and I'm initializing a priority queue. So since we by default this follows the minimum heap property, since I need a maximum heap, I'm specifying the order that it should follow maximum heap. Okay. Now next step here is what we have this written here for maximum heap. Create a maximum heap and add all elements. So you have created a maximum heap. Now let's add all elements to this. So when I add this, for int I equal to 0, n nems minus length I plus plus, I am adding all elements. pq dot offer of names of I. So I have added all elements to the heap. Now the heap creation is done. Now what we have to do? Delete k minus 1 times from the heap. Okay, I'll do that. Okay, I'm deleting it. Pole off. So after deleting whatever is the root element, that would be my kth largest elements, right? So I'm returning it. So I have deleted k minus 1 times. I'm returning it. Let's run. Okay. Yeah, sorry, there is a compilation error here. So if you see this one, 3, 2, 1, 5, 6, 4, k is 2. Second largest element is 5, right? So my output is 5. So this is using the maximum heap. Now let's do this using the minimum heap. I'll remove the solution completely. So first, for the minimum heap, what are the steps we have to follow? Create a min heap of size k. Okay. Now I'll do this. I'm creating a heap here, minimum heap. Then what we have to do? Initialize the heap with k elements. Let me initialize with k elements. For int I less than k, I plus plus, because less than k. So I'm initializing my heap with k elements. Now this is done. For the remaining k minus 1 element, what we have done, you compare the peak element. You compare the peak element, right? Whenever the peak element is lesser than the current element, then only you swapped it. So we have to do the same thing. For int I equal to k, because till k minus 1 we have initialized heap, right? So I'll do from k less than nems minus length I plus plus. I have to compare the root element, right? So pq dot peak off. So if the pq dot peak off is lesser than current element nems of I, then only you have to remove that. You have to remove that. And then you have to add a new element, right? So we have done this. So after doing all this, whatever lies at the peak would be my answer. So if you recap, first I have created a heap of size k. This is a minimum heap. And then I initialized heap with k elements. So I have done that. I have initialized it. For the remaining k minus 1 elements, what we have done is, if the root element is lesser than the current element, then remove the root element and then add a new element, because the new element is bigger than this. Okay. And after completing all this, whatever lies at the root, that would be my answer. Now let's run this. Yeah. So I have got the correct answer. Let me submit this. Yeah. This has passed all test cases. In the That's it. Thank you. In the coming videos, we'll solve more problems, hard problems.